Have you ever wondered why some processes, like an ice cube melting on a warm day, seem to happen all by themselves, while others, like separating salt from water, requiring a lot of effort? What hidden rule governs whether a change will occur naturally or not? Well, the direct answer lies in a powerful concept called Gibbs Free Energy. Often represented as delta G, this thermodynamic quantity is the ultimate predictor of whether a process will happen spontaneously at a constant temperature and pressure. Simply put, if the change in Gibbs free energy, or delta G, for a reaction or process is negative, then that process is spontaneous and will proceed without continuous external energy input. The core mechanism behind this prediction is the interplay of three fundamental thermodynamic factors encapsulated in the Gibbs free energy equation. Delta G equals delta H minus T delta S here. Delta H represents the change in enthalpy, which is the heat absorbed or released during the process. A negative delta H means heat is released, making the process exothermic. Next, delta S is the change in entropy, a measure of the system's disorder or randomness. An increase in disorder, a positive delta S, favors spontaneity. Finally, T is the absolute temperature in Kelvin. The equation shows that spontaneity is favored by processes that releases heat and increase disorder, especially at higher temperatures where the T delta S term becomes more significant. To use this knowledge in practice, you can calculate or interpret the sign of delta G if you know the enthalpy and entropy changes for a reaction. Along with the temperature, you can directly determine if it is spontaneous. For example, if a reaction is highly exothermic, meaning it releases a lot of heat, and also increases in disorder, it will almost certainly be spontaneous. Conversely, if a process is endothermic, absorbing heat, and also decreases in disorder, it will typically be non-spontaneous. You can also strategically adjust the temperature to shift the balance, making a non-spontaneous reaction spontaneous or vice versa, especially when the entropy change is significant. Understanding Gibbs free energy provides an elegant framework for predicting the direction of change in virtually any system, from chemical reactions in a test tube to complex biological pathways within a cell. It is also crucial for engineers designing processes, as they need to know if a reaction will proceed on its own or if energy input, like heating or cooling, will be required. Furthermore, a delta G of 0 signifies that a system is at equilibrium, where the forward and reverse reactions are happening at equal rates, with no net change occurring. Ultimately, Gibbs free energy offers a universal criterion for spontaneity by cleverly balancing the drive towards lower energy, represented by enthalpy, and the drive towards greater disorder, represented by entropy. It tells us not whether a process is fast or slow, but simply whether it can happen on its own under given conditions. By mastering this concept, you unlock a deeper understanding of why the world around us changes the way it does, making you a true expert in the fundamental principles governing all physical and chemical transformations.